All right. Hey, Harut, how are you?
Good. How about you?
I'm good. So it's showing that we're live
All right.
here on Facebook for Boost Your Knowledge number 3. This topic we are going to do covers turbine housings and a lot of stuff revolving around the exhaust and hot side of the turbo. So I've seen some of the material that you put together. It's very good. We're going to cover a lot today. And yeah, but before we get started, we're going to give a few minutes to let some other people join before we get into this. But I will say that we're going to do the presentation first for the first half or the first section of this of the Facebook Live, and then we'll get into any questions anybody has at the end of the presentation. So for those joining, if you do have any questions you want some engineering support and answers from, then please just type them into the chat box, and we'll get to that at the end of the presentation. After the first section of this of the Facebook Live, and then we'll get into any questions anybody has at the end of the presentation. If I can figure out how to mute this.
Yeah, it was repeating itself.
All right. How's that? Can you still hear me here, Harut?
Yes, that's good.
Okay. All right. So we've got a few people in the group now.
Yeah, welcome everybody.
Harut, do you want to just go into your background a little bit for those who haven't joined any of these topics before? How long have you been with Garrett, and what have you been doing over the last, I think, 15 years that you've been with the company? What have you been up to?
Yeah, it'll be 15 years that I'm with the company pretty soon here. Started off actually as an intern in the aftermarket group. So we do have different groups within our company, obviously OEM, aftermarket, motorsports, dealing with different customers. So I've been an applications engineer. We did a lot of off-highway applications, so working on John Deere applications, so turbochargers for OEM customer John Deere. So a lot of tractor applications, worked on Caterpillar, some of Ford applications like the 6.7 liter. Done a lot of, but mostly off-highway. Learned a lot of things there, and then jumped back to the aftermarket group about 6-7 years ago. So it's been a good ride. A lot of fun, learning a lot about turbochargers. Still learning. There's always a lot to learn. So it's been a fun ride for sure.
Yeah, I agree. I think, just with 5 years here with Garrett, and in those 5 years we've launched GTX Gen 2, G Series, and GBC. So it's never ending. The technology continues to progress, especially in the racing and performance side of the business. So there's always new things to learn, and that's really the reason why we are getting these Facebook Live, the Boost Your Knowledge sessions going to help with the understanding of all the complex topics of turbocharging. So yeah, I'm happy that you're able to set aside time to do this with us and everybody that's joining. So yeah, thank you for being able to do this.
Yeah, thank you for setting it up, and good to share the knowledge, right?
So yeah, again, hey Ezio, he's online right now. Good to see you. Before we get started, again, if anybody has any topics they want us to answer, we're going to do that at the end of the presentation. So just type what your question is into the chat, and we'll go through those at the end of the presentation. But to kick this thing off, we really wanted to get into a couple of new product launches that we just have released. So GBC is Garrett Boost Club line, and these are small displacement turbos that were designed for recreational vehicles, personal watercraft, UTVs, and small engine displacements. You can see the slide on the screen. There's 4 turbos in this product lineup, and they're all internally wastegated. They're calibrated and complete turbo sets from the factory. And the smallest one is a 0.4 liter to 1 liter. And the largest one is a 1 liter to 2.5 liter. So you can see the different engine displacement ranges and horsepowers there on the screen. So these are journal bearing turbos, and really just a filling a niche that we didn't have in our product lineup, right, Harut? Just the really small, almost micro-sized turbo range.
Yeah, exactly. So new aero, basically, you have more power in a smaller package. So definitely filling a need there for a lot of the smaller displacement applications.
Awesome. Okay, and yeah, these are available now. They are available worldwide. And to contact any distributor, we have the distributor locator on the website. If you go to the where to buy, you can enter your zip code and it'll pull up any of the local distributors that you'd be able to contact. And on the next slide, we did just launch our 2-liter Volkswagen Power Max. So 2 different turbos. It's a stage 1 and a stage 2, using 2 different Garrett products, a GT22 based turbo for the stage 1, rated for 485 horsepower. And the stage 2 is using a G25 660, which is rated up to 600 horsepower. Very cool and exciting new product launch for us here. The application list is in that table. So a lot of different Golf and a few different Audi applications for that. But that's pretty cool to see the G25 being used in a direct drop-in fitment. I think that's maybe our first turbo that's been used from like the G series lineup into a drop-in, I think.
Yeah, I believe so as well. So yeah, I think you can find more information on the website and through the distributors as well.
Yeah, definitely. Okay, and a pretty cool picture there of a little Golf R. So yeah, for the Power Max line, for those that aren't as familiar with it, maybe just to tell you a little bit about Power Max, these are, like it says on the slides, direct fit performance. So we engineered it to drop right in place of the OEM turbo, meaning that all the connections will line up with the OEM product. And a lot of times you're using some of the same hardware, but if there is a different O-ring or a different bolt, that is provided in the box. So what we do is we provide the hardware, and then depending on your tuning and calibration and the other modifications done to the engine system will depend on the results you get out of the turbo. But the turbo itself is capable of the power numbers you see on the screen. So pretty cool. Pretty cool 2 new options for that Volkswagen there. All right, so I think we're ready to rock, Harut. Why don't you start taking us through the rest of the info?
Okay, yeah, well, welcome again, everybody, to today's Facebook Live session. We'll be talking about turbine housings, basically different types of materials, different types of turbine housings, A over R, and how to try to match your turbocharger with the right turbine housing for your application. So what is a turbine housing? A turbine housing, what it does, it directs exhaust gas to the turbine wheel to spin the turbine wheel and eventually create power to your engine. So the exhaust gas flows through the turbine housing and into the turbine wheel. Depending on the type of turbine housing, you have internal wastegate, as shown on the top right. You have an internal wastegate with an actuator. So the wastegate is integrated into the turbine housing. You also have external wastegate types of turbine housings, which means it's called what we call a free floating or a non-wastegate turbine housing. So you still will most likely have a wastegate, but it's an external wastegate. So you'll still need to be able to bypass some of the exhaust gas through the turbine wheel. With the wastegate, it's just done separate from the turbocharger. So you also have different flange types, different types of turbine housings to fit different types of exhaust manifolds, right? And it really depends on the size of the turbocharger itself. Will depend on what kind of different options you have. You do have V-band throughout most of the range of frame sizes. Different turbochargers will most likely have a V-band option, but like the G25 will have a T25 option. The others will not. You'll also have a T3 option for up to like the 35 turbocharger frame size. And then you also might have T4, you might have divided or twin scroll. And then the much larger turbochargers will have, let's say, a T6 option, which is a really large 4-bolt flange. So it just depends on what kind of manifold you're mating it up to, what do you have available for, let's say, your application, and hopefully we'll have the flange size that fits your application, right? You also have different materials for the turbine housings, ranging from ductile iron at which has a limit of 800 degrees Celsius, resist up to 950 degrees Celsius, and stainless steel, which is on the newer G series. On most of the newer G series turbine housings, you have stainless steel rated up to 1050 C, which the material is also, in terms of ratings, you match it up with the correct turbine wheel, right? Stainless steel, we normally use that with a MARM turbine wheel to give you a 1050 C rating, right? And these ratings are intermittent temperatures, so it doesn't mean you can run 1050 C all day long. It's just a short period of time that you can run to these temperatures. And let's say, ductile iron, you can probably run a little higher, but we don't necessarily recommend it. But in short, let's say, in a short period of time, it's acceptable. So, and most importantly, burst and containment. All of our turbine housings and turbine stages are burst and containment qualified. So that means in the unlikely event that you have a turbine wheel bursting, let's say exploding into different pieces, we run a burst and containment test before the release of these turbochargers to make sure that the turbine wheel is going to be contained within the turbine housing. So very, very important for customer safety. Anyone around the vehicle, make sure in the event of something goes wrong that the turbocharger will contain the turbine wheel in the event of a burst.
Yeah, and that's a good point, because the turbine wheel itself is so much more dense and heavy than a compressor wheel. So that means it has much more energy. And when those things, Harut, the turbine wheels or the wheels, the shaft wheel assemblies in some turbos is going up to 300,000 or close to 300,000 RPMs on our smaller turbos, but the large ones, maybe limited to around 100K RPM. So yeah, the energy that comes out of that, if something does happen, is massive. So it's really important to understand that having a contained housing is on your vehicle. It could, it's just, it could mean a lot of damage to the engine, to fuel lines, to a tire. There's a lot of risk if you're not using a housing that's tested for containment.
Yeah, exactly. And it's a function of speed, and then also the inertia and weight of the turbine wheel itself. So the larger turbine wheels have more inertia and weight. So it's all a function of that. Very, very important that also the speed limits of the turbochargers are, let's say, you follow the speed limits and you don't go over very often. Very important, because the more the more you overspeed the turbochargers, the less reliable they will be, and high risk of, let's say, failure. So that's very important to abide by some of these turbocharger limits, like the turbine inlet temperature limits that are shown on the screen for each material, and also turbo speeds, which you can find on our website on the maps, the
Yeah,
compressor maps.
on the compressor map, you have those kind of vertically curved, I'm sorry, the horizontally curved lines that have the, what is there, usually 8 of them?
Usually seven speed lines, and the top speed line is the recommended speed turbo speed limit.
Yeah, great. Okay, cool.
Okay, let's talk about one of the important, let's say, numbers. One of the important ways to identify a turbine housing is the A over R. So that's area over radius. The area is located near the inlet of the turbine housing, and that area divided by the radius from that center line to the center line of the turbine housing where the turbine wheel goes into, that denotes your A over R number. And that A over R is on the website when you look in at different types of turbine housings, so you can identify them. We also usually have it's cast into the inlet of the turbine housing, and sometimes on the outside as well, so you can identify the A over R. So the A over R is let's say a sign of how the turbine housing will perform, and that's something let's talk about in this slide. So you have different types of A over R options for each turbocharger, right? You have small ones, you have large ones, and so fixed geometry turbos compromise between response at low engine speeds and maximum power rating, depending on the size of the A over R. So the A over R is also what we call the nozzle size. So with a smaller A over R, what you do is you maximize the gas velocity into the turbine wheel for maximum response. So with the smaller A over R, you have less exhaust gas to fill that area. That means your gas velocity is higher. So you'll be able to spin up the turbocharger much faster. So the issue with the smaller A over R is the lower mass flow may strangle the engine at high output engine RPM, reducing the maximum power potential. So with the smaller A over R, your compromise is lower horsepower potential, but you'll have the best, let's say, time to torque, best response, because the exhaust gas shown on this image on the right, you'll see it enters more tangentially, so you have a smaller angle entering into the turbine wheel to give you maximum response. On the other hand, you might have a larger A over R, so a larger nozzle size that allows for greater gas mass flow at high engine RPM. So you do have you have more area, so you have more exhaust gas flowing through the turbine housing, and that enters the turbine wheel more radially at a larger angle. So give you the let's say the maximum flow possible for that turbine wheel, so that turbine stage. So the drawback with this is the opposite. So you'll have relatively poor low speed response. So your time to torque will be a little longer, but you'll have maximum horsepower potential. So this all depends on your application, what you're trying to achieve. Are you trying to achieve the best time to torque, or you're trying to get the maximum horsepower possible out of the turbocharger? And we do have different sizes available. We have small A over Rs, large A over Rs, something in the middle. So you can you can choose the best for your, let's say your engine, your displacement, what your application is going to be. So let's take a look at how that affects the turbine map. So on the screen is shown a turbine flow map for a turbine stage. You can see the pressure ratio is on the x-axis going from 1 to 3, and your turbine flow in pounds per minute is on the y-axis going from 0 to 25. So you can see the two different A/R housings. This is the same turbocharger, but you have a 0.64 A/R turbine housing and shown in blue, and the 0.86 A/R larger A/R shown in red. You can see that the red turbine housing, which is a larger A/R, it flows over 20 pounds per minute. So that'll give you the maximum horsepower potential. But the blue turbine housing, the 0.64 A/R, is about 17, 18 pounds per minute. So lower, let's say, gas flow, maximum gas flow potential, so lower horsepower potential, but this will give you the better time to torque, right? Again, so depending on your application, what you're trying to achieve, you'll choose the turbine housing A/R based on that. So let's talk about different types of turbine housing. So you have, so your typical turbine housing is a mono scroll, right? You have a single scroll, single volute going towards the turbine wheel. You also have twin scroll, right? We have twin scroll options, which are mainly T3, T4, and the twin scroll has two volute sections in the turbine housing. So you can see this cross section here has not just one volute that's on the left turbine housing, shown on the left. The one on the right has two volutes. So this is called a twin scroll divided volute turbine housing. So this you use with specifically a twin scroll manifold. So you have to match it up correctly. You can't just take a twin scroll turbine housing and put it on let's say a non-divided manifold. You're not going to get any benefits there, because the twin scroll, let's say manifolds, the divided manifolds, they do have a benefit. So the concept is to divide or separate the cylinders whose cycles interfere with one another to best utilize the engine's exhaust pulse energy. So what this means is, you know, your engine's working. The example given here is a 4-cylinder engine. So you have the different strokes of the engine. So the firing order, let's say, of a typical 4-cylinder is 1, 3, 4, 2, right? So this means that as cylinder 1 is ending its expansion stroke and opening the exhaust valve, in the meantime, cylinder 2 still has its exhaust valve open, right? So in an undivided exhaust manifold, this pressure pulse from cylinder 1, so when the exhaust gas is trying to escape through cylinder 1, its blowdown event is much more likely to contaminate cylinder 2 with high pressure exhaust gas. So what this does is it reduces the efficiency of the exhaust gas going into the turbocharger. So what you do with a divided manifold is you group the cylinders together to keep them complementary. So you have 1 and 4 grouped together and 2 and 3 grouped together. So with the better grouping of the exhaust pulse energy, this will improve turbine performance and response. So with a divided manifold, you will have an increase in, or let's say decrease, so better time to torque with this divided turbine housing. It does have a little bit of drawback in terms of if you have the same A/R in a mono scroll and a twin scroll turbine housing, you will have a let's say you will choke out the twin scroll turbine housing first. So your horsepower potential for a twin scroll is most likely going to be a little less than a mono scroll. So again, it's a compromise of the similar to how you compromise between A over R, you're going to compromise a little bit on mono scroll versus twin scroll turbine housings as well. But there's definitely is a benefit to twin scroll for time to torque and increase in efficiency of the turbocharger.
So now somebody may want to utilize a twin scroll option, but let's say the manifold they have is divided or is not divided. I mean, you could still use it. It's just not going to effectively increase the response like a true divided manifold would, right?
Yeah, exactly. You're not going to get the benefits of a twin scroll turbine housing.
Yeah, and then somebody that's opting for a twin scroll setup, you probably don't want to use like the turbo at the higher end of its like horsepower range, because like you said, you may end up choking out before you actually reach that power.
Yep. Yeah, exactly. Our turbocharger ratings are for, let's say, the maximum potential of the turbocharger. So it really depends on what turbine housing you put on there as well. Putting the smallest turbine housing on a turbocharger and expecting to reach the maximum potential of the turbocharger is most likely not going to happen, because you're going to choke out that exhaust gas energy much sooner and you're not going to reach that potential. So typically trying to reach a maximum potential, let's say horsepower rating for the turbocharger, you would want to use the largest A over R typically.
And you may if you're drag racing, it's unlikely the divided setup is good for that.
Yeah, exactly. It depends on your application and use of the vehicle. Yep.
Okay.
So in terms of we're talking about different AVRs. Let's see how they ultimately affect the result on the engine, right? So this is a Dynograph shown of the same turbocharger. It's a GTX 3076R Gen 2 used on a 1.9 liter application on Chris Boersma's time attack car. So same engine, right? Same car, same turbocharger, just different A over R for the turbine housing. So you can see he used a 0.83 A over R and compared it to a 1.01 A over R. You can see that with the larger A over R, you gain 50 wheel horsepower, right? So you're gaining 50 wheel horsepower with the larger A over R, because you can flow a lot more exhaust gas energy through that turbine stage, through that turbine housing. With the smaller turbine housing, right, you're not going to reach that potential. You're gonna let's say limit yourself to 600 wheel horsepower, because you'll start choking out the turbine stage. You're going to start increasing your back pressure, your EGTs. So you do have to be careful with that. But the drawback is with the larger A over R, you can see, let's compare the two green lines, right? That's the power curve of the 0.83 is kind of shown on a dotted line. So you can see that the time to torque on the 0.83 is much faster, right? Up until, let's say, about 5,500 RPM, the 0.83 turbine housing is performing better. So you're going to have a better time to torque, and that's when it crosses over, and then the 101 A over R takes over and has a much, let's say, bigger area under the graph, which is ultimately what you're trying to go for. And you can see that there's a big torque difference as well, going from 400 to 475 with the larger A over R. So a real world application just to show how the turbine housing ultimately affects the decision that you make and the the goal that you're trying to achieve. So it's really going to depend on what you're trying to achieve, and each person's going to be different, I think.
Yeah, yeah, that's definitely a cool example, and there's a lot of those on the website, in various sections of the news on the website. What we tried to do is when when we look at our race teams that we're supporting, our race teams that are using the products, trying to make sure that that information is available to everybody to see and understand some of these case studies here on applications and how it's going to perform on a vehicle. So on the website, you can always use the search bar in the upper right to try to find some keywords and maybe a setup that you're using to find some more data. But yeah, so that's the last slide of the presentation, I believe, Harut.
Yes,
Okay.
yeah, it is. Yeah, I mean, like you said, there's a lot of information on the website that you can spend a lot of time to learn and increase your knowledge. And we always have our distributors as well, very knowledgeable, very experienced. They can help with matching. I mean, you can start with a boost advisor, and then talk to a distributor to, let's say, narrow down your decision and buy the correct turbocharger for your needs.
Definitely, yeah. Boost Advisor, it's a good tool to help match everything, and then distributors are the next step in that. They've got so much knowledge and experience to help refine your match, as well as give you some inventory and shipping times and costs and pricing on everything. So looks like we've got a few questions here. We'll go through these right now and try to get Harut's input on some of these. So Jameson Roy says, why do some turbos come with a lot of shaft play out of the box?
It depends on what you mean by a lot, right?
Yeah.
It depends on whether it's a journal bearing turbo or a ball bearing turbo. The turbochargers, when they come, they don't have oil in them, so that's affected as well. But in the end, as long as the wheel's not rubbing the housing, you're not going to have an issue, right? That's the worry about having let's say shaft play, is that if it's too much, it would cause a rub and then damage the turbocharger. So a rub between the compressor wheel and the compressor housing, or the turbine wheel and the turbine housing. Yeah. So yeah, once you add oil to the bearings, that's going to consume a little bit of clearance as well. So if you are showing, let's say, a lot of shaft blade, that will definitely reduce once you have oil flowing through the turbocharger and as it's spinning.
Cool. Yeah, so that pressure that's in it holds the assembly in place, right? Is that what's going on?
Yeah, exactly. So you have a lot of, like the oil consumes a little bit of the clearance, so you're not rubbing wheel to housing. Because the oil provides the damping, let's say, between the bearing and the shaft, or the bearing and the housing, and all the components inside.
Okay. Joshua Daniel, he just put together a G3900 reverse rotation setup for his STI. That's pretty cool. We'll make sure when you get it all going, or if you get it dynoed, tag us in your social media links, and we could potentially feature it on our social media pages. Okay. Joshua also says yawn emoji for micro turbos. Yeah, I know, 0.4 liter to 2 liter stuff isn't super exciting, but there's, just imagine the UTVs and the snowmobiles and jet skis that these little GBC micro turbos can boost. So yeah, I think that'll be a unique segment also to see how those turbos are used in different small engine displacement applications. I'm pretty excited to see that. Okay, Derek says, are we able to answer questions that don't pertain to turbos? It's unlikely, but if you type in your question, we could see if we know any of that. Okay, so Ezio also is one of our sales guys out in Europe. But he says the Volkswagen Turbo, that new Power Max, fits the Skodas and the how do you say that? The Seats.
Seat. Yeah.
Seat. Okay. Also very popular. Okay. Josh Daniel was asking, is there a T3 and T4 V-band, or is T4 the square flange or the bigger divided flanges?
Let's go back to that picture. All right, so the picture shown here, the first one is a T25, so that's the smallest bolted square flange. The second one shown is the T3 flange. I think in the older, I think the GTX series, I believe we do have a T3 divided as well. And then we do have T4 divided for all the new G series. We might have T4 undivided for the GTX lineup. So we do have different variations for the different frame sizes. Was that what he was asking?
Yeah. So the picture does a good job. So there's going from left to right, like Harut said, T25, T3, T4, T6 is the largest, and this does just reference the I guess you could say the square dimensions, the bolted dimension for those flange types. So you could know that if a kit manufacturer had a T4 manifold that they were selling, that our T4 turbine housing would bolt to it. And regardless of whether that was divided or open, that T4, because it's the T4 is basically identifying the bolt dimensions of that flange, whether it's open or divided.
Yep. Yeah, and the T4 is bigger than a T3, so it's gonna flow a bit more for the large, let's say, maximum horsepower potential.
Yeah. So yeah, that's definitely key for identifying when you're buying a manifold or trying to find a turbo that fits an existing manifold. The bolted flanges are identified by the T, and then the V bands are all different sizes. So there are flange diagrams and spec sheets on each product page that you can go to see the diameter of the V band, and then the flange specs for whether it's T6 to T25. Those are available on the website as well.
Yeah, and you always want to make sure that the manifold you're buying is going to mate up to the flange on the turbine housing for sure. Because I think there are different V band sizes out there, so you do want to make sure that you're buying the manifold that fits the Garrett V band spec.
All right, thank you, Volute. Okay, so this one is something I may not know too much about, but maybe you can provide some input on this one, Harut. But ETS builds a V-band turbo kit for another brand turbo.
Yeah.
And some people on the line have said that the Garrett will fit, but the V-band inner ring doesn't fit back and forth, but they call it a T4 flange. So there may be some cross-referencing, I guess you could say, misunderstandings between some of these. But yeah, like for us, if it's a T25 through T6 type of flange, it's bolted, and then V-band is totally different, and then each series has its own V-band size. Some of them are grouped, so G25s to 35s use the same V-band inlets, and then the 40s and the 50s, 55s, those all have different sizes. So yeah, you definitely need to be able to match those up. And again, it's tough because the manufacturers as manufacturers, we want something that's consistent across our range of products. So,
Yeah.
but we don't, because we're competitors, we don't cross-reference what everybody else is doing.
Yeah, so
It-
yeah, you want to make sure, like you said, the flange diagrams are on the website. If you
yeah,
go to the specific turbocharger you're looking for, then you can double check and make sure that our turbocharger will fit that manifold for sure.
yeah. Okay, so the next question we have is, what types of turbos cannot be repaired?
I guess, what do you mean by repair? There's-
Yeah,
that's a broad spectrum, right? Depends on what you're repairing. Are you repairing just a turbine housing or a compressor housing, or you're trying to repair the insides of the turbocharger? Right, we build our turbochargers on an assembly line to product specifications, internal product specifications. Obviously, we can't share those. So if you're trying to repair something like that, and you're not, let's say, balancing it or torquing it to the right spec, which is usually the internal specs are proprietary. Unlike, let's say, so you're bolting a compressor housing to a center housing, we can share that information. But if it's like torquing a lock nut on the compressor wheel, or let's say press fitting something, that information is proprietary. So if you're trying to rebuild it, you're most likely not rebuilding it to the OEM specifications, which can eventually cause issues down the line.
yeah. I think the best thing for that is if you have a product that you're considering to have rebuilt, whether it's just looking at the bearing or something like that. Some of the distributors will perform that service, but you would need to contact them directly. Garrett does not, on the racing and performance side, we don't offer that service directly. So you would need to discuss that with your distributor and to see if they would warranty that process. Sometimes it's just easier to buy a new cartridge if you are that concerned with it. But I would say contact your distributor. They may be able to look at it and address any signs of wear and tear. Let's say, maybe the turbo was having a hot shutdown all the time, and there was a lot of coking around the shaft wheel assembly, and you're feeling like, oh, it's kind of rough. It's hard to spin this thing. Best thing again to do is let the distributors do it. These guys are the experts. Don't take it apart on your own, because
Yeah.
like Harut said, there's tightening procedures that should be followed, and it's not just it's not just something simple. It is a process that we have tried to define as detailed as possible. So yeah,
Yeah,
call a
yeah,
distributor for
exactly.
anything.
Distributor would be your best option. I think Limit Engineering is one of the distributors that definitely does a lot of rebuilding. So that would be your best option.
Yeah. Okay, so for a rotary application, twin scroll or mono scroll for best efficiency? Any recommendations?
Probably twin scroll for best efficiency, right? If you're looking for boost response, you want to separate the pulses from each rotor, then a twin scroll would be your best option as well.
Right. Does turbine A over R pounds per minute have a flow cap at 2 pressure ratio is the engine's peak torque RPM? Let's see. Does the turbine A over R have a flow cap?
Oh yeah, it has a, if you look at the turbine maps on the website, each turbine A over R does have a limit, right? I'm not sure if
Yeah,
that's exactly the
that's
question, but
yeah. So like you showed in the turbine maps, each one has pounds per minute and at a pressure ratio. So
yeah,
and these are all flow tested, right? When you're preparing a turbo to be launched, you're testing out each of the A over R's in the different combinations. You're really getting a lot of data to go with each product to give the most information.
Yeah, exactly. These aren't just just estimates. They're actually turbochargers that we run on a gas performance. We call it performance gas stand, and we're able to map out these flow lines, whether it's for the turbine stage or the compressor stage. That's why we have compressor maps for all our performance products. Is we do have we're one of the few in the world that have that capability, and we're able to share those maps with you guys, so you can help match your the turbocharger to your application properly.
Yeah. Okay. All right. So a lot of times on, let's see. So we have tech articles on the website as well. Tech 101, 102, 103. It goes from beginner to advanced to expert. And we do a lot about, we do a lot of discussions on compressor map matching for an engine based on horsepower needs or target horsepower. But how could somebody how could somebody find similar information or be able to really refine A over R of a turbine housing?
Yeah, I think we talked about this in one of the other sessions as well. It's hard to do that because you need a lot of data from the engine. So your car has to be, let's say, thermocoupled and pressure tapped, so instrumented with all these different things in order to be able to give us that data. So then we can properly run it through the calculations. Otherwise, everything is an estimate, and it's better to just look at your application, what you're trying to achieve, and choose the right turbine housing. And like I said, the distributors have a lot of experience with that. Um, so that's in order to pinpoint it, it's not something that anybody can, let's say, give us the proper data unless you're an OEM customer, is when we typically get that type of data. So unless you have your whole engine instrumented, where you're most likely not going to be able to get us that data, and everything's going to be a rough estimate, which might give you a wrong answer in the end anyways. So
Yeah, times trial and error is the more productive solution for the turbine housing question.
yeah. And the distributors have a lot of experience in terms of matching. They've seen, you know, they've seen a lot of different vehicles and applications. So they would usually know which AVR is best for your needs. You just have to make sure you communicate what you're trying to do with the car in order for them to help you out better.
Yeah. Okay. All right. Hong Nguyen is asking if we have a stage 3 Power Max for Volkswagen planned. And I'd say at the moment there is not one that we are planning, there's not one that's available. But you can always check back with the website or contact a distributor, and they may have something that meets your needs that uses a Garrett product. So let's see, Derek is working on a 94 Accord and believes the shift linkage from the shifter to transmission broke. Oh, this is the question that doesn't relate to turbos. Can't get it back into gear, and it won't go back into neutral, and it's stuck in the gear he put it in. I would say get it towed to a local shop, and they can probably figure that out pretty quickly. Okay, so
Yeah, I don't have anything at this.
okay, Danny Wright is asking, what's the ideal turbo size for a 13B to produce roughly around 400 wheel horsepower? We kind of went over some rotary match info last month on the call, but I'd also say another really good resource and tip, Danny, is taking a look at what Rob Dahm has done and what Rob Dahm is doing with all of his videos on YouTube. Because everything on that channel is rotary based, and he's run. I think the smallest turbo he's put on is a GTX 3584 RS, and he's run everything up to even a G57. So there's a lot of really amazing data on his channel. But Harut, anything you would recommend off the top of your head?
My guess would be like a G30, a 35 size turbo, probably.
Yeah, the 400 wheel. Yeah.
Yeah.
Okay. Reinhard is asking, so would smoothing out the internal volute surface aid in gas velocity?
It does, but not as much as you would think it would help. It's probably not a noticeable difference on in horsepower output.
Okay. Okay, let's see. All right, so there is a question here, is what's the nominal, or I'm sorry, what's the normal safety margin to failure for turbo speed? Let's say somebody was lost an intercooler pipe and turbo RPM spiked. Is there anything we would say that is like a normal percentage over in which we would feel like that the turbo would be, you know, unharmed, I guess, or okay to continue using? Which is, I'll first say is it's a tough question, unless you can accurately, unless you have a speed sensor, let's say, that's measuring your RPM shaft speed. So if that's the case, if you do have that, then what would maybe be some signs of where, or anything that somebody could look for if that did happen? So we don't have a percentage that we're going to
Yeah.
say like it's okay to go over this, but what would be, let's say, what would be the actual concerns if that happened? I mean, would we, do we want them to contact the distributor to see, have the distributor take that, take it apart, look at it? Are there any areas where they would see some stress or anything to look for, like maybe the wheel might touch a housing or something like that, that somebody could look at?
Yeah, I think that would be the number one sign in terms of having overspeed. There is no, I guess, specific percentage, because each wheel, each compressor wheel, each turbine wheel, and sizes as well, they all have their own different fatigue life, let's say. So it depends on how much you go over for each frame size. That has to be looked at specifically. So yeah, we definitely don't recommend going over, but if by chance something goes wrong, and it does, yeah, you would try to take a look at if there's any rub between the wheel and the housing, and if the shaft play is really excessive, let's say compared to as it was originally. So that's something you would try to take a look at.
Okay, perfect. Thanks, Harut. So the next question is, all right, next question is, what's the horsepower differential between piston engine and rotary engine on a given horsepower? I know we touched on that in the last one. So Danny, you can also go back to like our live videos and kind of scroll towards the end. We did touch on rotaries on the last one. I know we referenced Rob Dahm a lot. That is just because he does have a lot more experience, like real life experience with the rotaries. And there's so many different combinations and the different port types that can really change how, how the exhaust gases are flowing through the turbine, which can limit the actual performance of the turbo. But yeah, Harut, any thoughts? Any thoughts to add to that?
Yeah, I mean, like we said, rotary has a lot more exhaust gas flow, so you typically do go with the larger, let's say, larger turbocharger for a match.
Okay, perfect. And yeah, and that's it. That actually rounds out all of our questions, I believe, unless there's anything else.
That's great. I mean, thanks for everybody for joining, listening in. It's always good to learn more about turbochargers for sure.
Yeah.
Yeah. And hope everybody comes back for the next session, right?
Yeah, so the next session will be about a month from now, or about 4 weeks. We'll put some more materials together, and definitely we'll set up another Facebook event so you can see that in advance, a couple weeks in advance of when we're going to do it. But we'll look at the schedules here and find a good time and day. The other thing too, for anyone that's still on, if there are any topics that you would like us to cover, put them in the chat. We're going to go back through and look at all this stuff, but we're always interested in knowing what you want to know a little bit more about from an engineering perspective and a discussion perspective. So because we try to keep these around a half-hour presentation, a half-hour of Q&A, give us some suggestions, and you never know, we'll probably include that in some of our future topics here. So Harut, thank you for joining and putting all this together. It's really awesome to have the expertise and knowledge of this, and to even myself, I come away from these knowing more. Yeah, thanks for sharing your knowledge there. Yeah, anything else you wanted to add before we close it out?
No, that's it. Thank you, Tim.
Okay, great. I appreciate it, everybody. Thanks for staying with us for so long, and we will catch you on the next Boost Your Knowledge.
All right, take care.
Thank you.